Hello, everyone. I'm still not very good at this whole talking to thin air, but I think I'm just going to wing it as I usually do with, just kind of everything and just see how this goes. I've been working a bit on topology, and I've been sort of reading the first 20 pages of the notes written by, was it John Smiley, something like that? He's my lecturer. He wrote the this year's notes on MA3 F1 Introduction to Topology, and I don't know. I just decided, yeah, I'll write my own notes kind of based on it, and give some intuition about some of the stuff that actually goes on. So I think I covered about 20, like, I don't know, 20 pages if you look at it as a PDF. It's like 16 pages if you look at it as his page numbers on his notes. But suppose if you have his notes and you like his, I guess you can follow along, and I might just shed a bit of intuition. They're more or less kind of parallel with one another. And I think I more or less understand everything so far up to definition 3.7, which is about deformation retracts. It's currently about like 11:43, and I'm a bit tired, so I didn't actually I didn't cover like just the more subtle areas afterwards, which was about how F1 can define a retract by an inclusion, but I couldn't quite pinpoint how to explain what I think I understand about that. Now, I just want to point out that I am still only a student, so I am going off of his notes. So either I make a mistake, or I've copied a mistake and I have some bad understanding, or it's just, I don't know, straight up my mistake. I might say something that's wrong, but I hope that at least in some sense I can give a decent intuition as to what's going on into this course. So I guess if this is helpful, we can get on with it. So I guess we could start talking about the preliminaries, and the preliminaries should be at least enough content about. Well, okay, if you did norms, metrics, and topologies as a math student at Warwick, that has more than enough content, and metric spaces has more than enough content because they're practically the same module. But there's information in each of these areas that I suppose is really integral to be able to understand what's going to happen in this module specifically. Now, I'll just go give a quick idea as to what's really supposed to happen in this module. You're supposed to use the ideas that you developed in point set topology, which is what you studied last year, and you're supposed to interpret it to sort of classify shapes up to homeomorphisms. If you don't know what a homeomorphism is, don't worry. I'll be going over that in these preliminary sections nonetheless. I'm going to then cover a bit more. I'm going to talk about some ideas like gluing, talk about what a retract is, what a homotopy is, and a deformation retract. Actually, I won't be covering a homotopy today, but we'll be starting that sort of section. So, yeah, let's start talking about the preliminaries. I have this little window open, by the way, just in case I want to draw something or work through an exercise or some idea. And obviously they're night and day, so one of them is notes and the other one's intuition. I'll be putting the notes in the description, but I'm going to be updating them as I go because I'm still writing my own notes, of course, because I'm revising as we go. Definition 1.1. A metric space is a set X with a function that satisfies these three properties. And I draw a little picture down here about like what this is supposed to mean. So you have some space X, right? And you take any 2 points, you can establish a distance function between them. So d of x, y. The three properties are just the sort of things you'd expect a distance function to have. So for example, distances aren't negative, those are displacements, okay? If you do physics, I suppose that would make more sense. So here, distances are always positive. So the first property is that, well, okay, non-negative. The distances are non-negative, and distances between 2 points are 0 if and only if they're the same point. I.e., if I'm walking from, I don't know, some house, right, and to another house, and I say, hey, I walked 0 meters. Okay, well, yeah, 0 meters between them. I'm doing that. Hey, that's my name, Om. Then if I had walked between them, and I walked fucking 0 meters between 2 houses, they're the same house. So it's the same point. Then it says that the distance from x to y is the same as the distance from y to x. Now, obviously that makes sense under the same sort of intuition. If I have 2 houses, let's just bring that along again. If I have 2 houses, then the distance to go to here and the distance to go to there should be the same. And the third one is the triangle inequality, as people usually like to call this. So that's the distance from x to z is less than or equal to the distance from x to y and then y to z. So let's say this is like house x, that's house y, and that's house z. Okay, so let me draw one more house like that. Okay, the distance from here to here, sorry, put z there. The distance from here to here is less than the distance from here summing up with the distance from here. And obviously you can see that this is just sort of like literally the triangle inequality. If I went from this point to this point and then to there, it is a longer path than if you had gone just directly to that point. So yeah. So that's really what a metric space is. The thing about metric spaces that are important is, well, okay, they are a subsidiary of what are called the normed spaces, because every norm defines a metric. Norms are just sort of like length functions. They tell you how far away you are from the origin in some sense. For example, this here is like norm of x. It tells you how big x actually is. But you can also use a norm to define a function, a distance. For example, if you have 2 points, x and y, in, I don't know, the real numbers, I suppose, then the distance between x and y is the difference in x and y, and you just subtract them. However, if you did something like with coordinates, x1, y1, x2, y2, there's many ways of defining a distance between them. So, for example, the distance here would be the 2 norm on this, and that's just the difference in x1s. Well, the difference in x's squared plus the difference in y's squared square rooted. So maybe you don't remember what 2 norms are or what p norms are in general. But for this course, I don't think we really need to understand what norms exactly are. We just have to know that you can at least, given any norm, define this thing, which tells you a distance from 2 points. So yeah, that's a metric space. It's quite straightforward. So there's examples such as Rn, which is just vectors with n entries, or as I like to think about it, R3 is sort of like 3D space, so Rn is sort of like n space, like n-dimensional space. Obviously it's n-dimensional. If you do any linear algebra, you'd know Rn is n-dimensional. Continuous functions on the bounded interval 0, 1, and the distance function would just be this integral thing. So, I mean, I recommend trying to actually see that you actually get these properties. I haven't written them out, and I haven't even said it as an exercise, because checking if things are a metric is not too complicated, and it should be something that you're expected to figure out just by reading the definition out, and writing them out. So, moving on, in a metric space, XD, so we obviously pair, we use this notation x comma d to be the space x, so the metric space x with its distance function, its metric, D. So yeah, in a metric space, XD, we define this B thing by B of X comma epsilon to be this set. Okay, and we for some reason call it the open ball of radius epsilon around X. Okay, this here is just a bit of formality I wrote out. You can kind of ignore it, or you can read into it and check if I'm right or wrong. I don't really mind. But what does this really mean here? What is the open ball? Well, let's read what this says. It says all the points in X such that the distance from Y to X is at most epsilon. Okay, so if I thought about, I don't know, distances regularly, if I said, I don't know, epsilon is 1, for example, then if I don't know, was in R squared, so the Cartesian plane like this, X and Y, and I don't know, maybe my X is going to be equal to the coordinate 0, 0 there, then, and I don't know, D was supposed to be just the norm distance, the regular distances between 2 points, the one that I defined earlier where it says the literal Euclidean distance between points, then all of the points that are distance at most 1 away are points that are sort of at most, well, okay, if they're at most 1 away, they could be less than 1 away. But things that are exactly 1 away are things that lie sort of this distance out, where this is 1, right? And obviously, just kind of by looking at this sort of radial pattern emerges. And you should be able to put 1 and 1 together that it would just be the space of points that sort of lie within this circle. Now keep in mind very carefully that it's an open ball because we do not allow equality here. If we had equality, we'd call it the closed ball, but we don't really need to understand what closed balls are, at least right now. I do norms, metrics, and topologies, or metric spaces in second year, if you have the ability to, or you could look over those notes. But I'm going to assume that the notion of a ball is quite straightforward. Obviously, the kind of ball that you have varies with the kind of metric that you have. So, and balls only really make sense in a metric space because balls require a metric to define them. Balls don't make sense in a topological space, open sets do. In fact, that's kind of where we lead on to. So definition 1.2, in a metric space XD, we say U, a subset of X, is open if for all points in U there exists a epsilon greater than 0 such that the ball around X of radius epsilon is contained in U. A subset V of X is closed if and only if X minus V as a subset of X is open. Okay, I'm just going to do myself a solid and put myself on Do Not Disturb so I don't get any more random notifications. Yeah, so let's look at this carefully. Well, what it's saying is, I have this nice diagram here actually, I might just use this. So here's my space X. X is the most outermost space. U is some, I don't know, set inside. And I want to describe that the point, well, I want to say that this set is open. Well, how do I describe it's open? I take any point, so here I took the point X in the middle down here, and I said, can I find a little ball around it that entirely lies inside of U? And I drew this one. Now remember, this boundary thing that's kind of touching it, the boundary isn't included in the set in the open ball, so it's not really inside. So it's not really touching U. I mean, it's very closely touching U. If you threw in the boundary, I suppose, then it would touch you, but it's not. So we're good. And yeah, so I threw a little ball around it, and I seem to be okay. The point is, if I can do that around every single point inside of U, so if I took, I don't know, maybe this alternate point there, I could take a small ball that's kind of like that around it, and we're good. If I took a point there, I could take a small ball like that around it. Okay. Because I can do this with the set U, we call U open. And I gave this little bit of intuition. Here U is open. If U is open, it usually doesn't have a boundary. And the idea is if you did contain maybe your boundary, maybe you have this solid little part down here, right, inside of this closed space here, and this is maybe your topological space X. So I'm going to call this U, but I'm going to show that this is not open. If I take any ball around this, right, of any size, then there's going to be a section of it that's not inside of my open set. So, well, not inside of my set U. Whereas if I was just off barely, I could still put a tiny little ball around it and we're still inside. So whenever you have an open set, it's a good rule of, and you can understand it, I suppose, in a metric space, there is no sort of boundary left. You kind of omit the boundary. So you could think of it as a basketball, but only, well, not the basketball's outer surface, just the air inside of the basketball. That would be an open set. But the exterior of a basketball, okay, I was talking about a basketball earlier actually, and someone pointed out that it's got a hole in it. Just ignore me when I say that ignore the idea that there's a hole in this basketball, right? It's just the air inside of a ball, okay? That's the ball. I said ball so much. Okay, so here's some examples. Obviously, in R, you could take balls to just be open intervals. And, well, okay, you could just take the union of a bunch of a union of a bunch of open intervals, and you're going to end up getting stuff that is open. There's like this entire theorem that says if you take the arbitrary unions of open sets, you get open sets. Finite intersections of open sets is open. The empty set, the whole set are all supposed to be open sets. There might be something else, but I can't think of anything. Yes, in fact, I actually mentioned it here. We say X and the empty set are trivially open and closed. So it is possible to have open and closed sets. I think they go by Clopen sets or something like that. But I'm just going to try and avoid confusing you because it's not really worth investigating Clopen sets unless you're talking about, I think, connected spaces and stuff. I mean, being connected and the notion of connectedness is very heavily covered in second year metric spaces or topologies, so I really recommend looking into that if you don't fully understand the idea of connectedness. I might go over it. I'm not sure if I mentioned it in my notes, or in his notes, but nonetheless, we can continue. So yeah, here's a different metric that you could use in R squared, and that's just taking the maximum distance between x coordinates. Now here I've drawn a diagram for the ball around the center point. So here 0 is actually supposed to be like 0, 0. But because I'm lazy and Mario Mikhailov was my lecturer last year, I just omit vector symbols and I just use context clues. And 3 here is literally 3. It's not 3, 3 or something like that. Here the ball is sort of like a little rectangle, like a little square around the center, and well, you know, that's something. So somehow a ball kind of looks like like a square minus its boundary, but you wouldn't really call a square minus its boundary a ball. Only a mathematician who's smoked a bunch of crack and decides to talk to his friends in second year about open sets will be like, yeah, you know what, that square is kind of ballish to me. Alright, definition 1.3. A topological space is a set X with a collection of subsets X, omega, such that the empty set, the set itself, is in the set. Okay, but maybe it's hard for me to have said this all out loud. Here it's basically saying that both the empty set and whole set is supposed to be. Why am I saying this? You can read this, of course. The most important part is that we say that omega is the collection of open sets of X. Their complements are closed in X. So this omega thing here is supposed to be the set of open sets. And obviously, I just said trivially the empty set and the entire set itself have to be open. So they lie in the omega. If you have arbitrary open sets, then arbitrary unions are are open, so lie in the set. If you have two open sets, the intersection of open sets is open, and in fact this actually implies inductively implies that finite intersection of open sets is open. So we get all the properties that I sort of wanted to have about open sets that I said was a theorem in metric spaces, but inherited in a abstract sense, because in a topological space you sort of omit any concept of metrics or distances or stuff like that. You only care about the properties of open sets. So the idea is that, as mentioned here, the idea is that all metric spaces are topological spaces. Definition 1.4, let x comma omega be a topological space. So in the same way as we did before, we, rather than saying that x comma d is a metric space, I'm going to say x comma its topology, the set of open sets is the topology. We just say the ordered pair of that is a topological space. A neighborhood of x in a set n is a set n such that there exists U in the topology where x is in U and U lies inside of n. Okay, so it's kind of crazy what it's saying, but and it might be a bit tricky to read, but what it's kind of saying is you could, like, a set n is a neighborhood if it surrounds x, and that you can take an open set around x that lies in n. So sort of maybe if you build it up, you take a point x like this, right? Remember, this is all kind of lying in some x space, some topological space x. This is a neighborhood, right? If I can do this around it, okay, and say, hey, you know what, that's open around it. So basically, you could kind of say all open sets are neighborhoods. I think they call that open neighborhoods, but a neighborhood is a bit more general because you don't need to even explicitly state that there exists. I don't know. I feel it just seems to be like an in-betweener step. I don't really know. If you have a neighborhood around x, you have an open neighborhood around x, but whatever. And if you have an open neighborhood around x, then it itself is a neighborhood. So I don't really know. It's a bit silly, but it's just saying that you can surround the point x with an open set. You could more or less think of this in a metric space sense, as you could just put a little ball around it. Open sets are just sort of the balls of topological spaces. Assume when using a metric space, and talk about topology, we mean the topology induced by the metric. So of course, the topology induced by the metric is just supposed to be the sets that are open with respect to that metric. So though one set can have multiple metrics associated with it and topologies on it that aren't associated with any metric. So I think at one point or another I end up mentioning, or at least I gained an example from reading the notes about how the set the set on R with cofinite topology is not first countable, and how every metric space is first countable. And that will argue that there's no metric on the cofinite topology. But yeah, I mean, I suppose that's going to actually supposed to be an exercise, I think. Did I mention that? Yeah, so exercise here. I was going to go over this one at one point, but I think it's a bit too easy. So I'd rather go over something that's a bit more interesting. Okay. So here I go over, there's an example where X is, the topological space is Rn, and you have these two different norms that define so it's x1 and x infinity, sorry, what is it? I mean, obviously you don't say x infinity. It's the one norm and the infinity norm on Rn, and you can use those to define these. You can use them to define these distance functions in the manner that I mentioned earlier. And due to this theorem here, so is this obvious to prove? I mean, I can give it a shot. So if you have the max of xi, that's what this x infinity is, I equals I in n, then obviously the maximum is going to be less than, okay, so if I'm taking the maximum of not just this, but the modulus of the xi's, then it's less than or equal to modulus of x1 plus modulus of x2 plus, because, I don't know, say in this case, modulus of xk is supposed to be the biggest one, then xk is somewhere in this summation here. And adding non-negative things to it only makes it bigger, which justifies this inequality. And in the worst case, everything here is at most the biggest thing that it could possibly be among this list. So, i.e., it's at most modulus of xk in the example that I said before, which is n times modulus of xk, because it's one for each index. So maybe I should state this. So then what this really says is that x infinity, like that, which is the maximum of all of this stuff, is less than or equal to, well, okay, this thing here is literally the x1 norm. Is less than or equal to, well, that's n times the infinity norm on x. And so you get this inequality that I stated here. Well, that was stated in the notes that I copied, obviously. So yes, there's this nice idea that if you kind of define balls using this, somehow you could trap a ball inside, well, a ball using a one norm inside of a ball using an infinity norm, and a ball using an infinity norm with a ball using a one norm. So I suppose that kind of looks like, so here's maybe my infinity norm ball, and that's a one ball, sorry, a one norm ball that I can use, so like that, and then I can fit another infinity norm ball inside of it. See, and I can kind of do this sort of thing kind of forever, where I just, so if you have an open set, of course, it just means you could fit one of these kinds of balls inside. So I can fit any infinity ball inside of any one ball, you know what I mean? It might be a bit cumbersome in the vocabulary. Indeed, two norms on a finite dimensional vector space always have the same topology. And I think that was a theorem proved in norms, metrics, topologies. It's I can't remember exactly how to prove it. It was a bit tricky, but it can be done. So let x be a topological space. A collection B of omega is a basis of the topology if for all u there exists a collection of B sub I that lie, B sub I indexed by some capital I, that lie inside of that set B, that collection, such that the union of those sets Bi actually give you any of those open sets that we mentioned earlier. We say a collection of subsets. B, fancy B, generates the topology omega if this fancy B is a basis for the topology. Okay, so the word basis gets thrown a lot around in mathematics, and it's usually just in linear algebra you use them to sort of describe how to hit every single point with linear combinations, using only maybe a handful of known values. Okay, specifically in finite dimensional vector spaces. I mean, there's some random mumbo jumbo stuff that happens in functional analysis with infinite dimensional vector spaces that I don't quite understand because I didn't do it. But you sort of, the intuition of a basis is the smallest, like a small collection of things that help you define the entire collection of objects. So here, bases are just sort of like these open sets that if you take arbitrary unions of a bunch of intersections, somehow if you do them in some random configuration, you just kind of end up getting any open set you really want for a specific topology. So, which is why I think the word generates is this word generates here is pretty accurate, because you just sort of like think of bases as just a small collection of things that just somehow can be used to literally generate things in the topology. It's a bit, maybe I'm being circular in using the word generates, but so be it. So example, open balls in metric spaces. This is kind of obvious because you could sort of think of maybe, I don't know, maybe you have this open set like this in some space. Then what you could think about it as like just a bunch of balls kind of like doing this. You just take arbitrary unions of them, and look, you kind of have, if you look at the volume encompassed by this, well, the volume encompassed by this can be used to describe this entire open set that I was using, well, that I drew through dashed lines. The topology itself forms a basis. Well, I hope that goes without saying, because if I take any u in the topology, then u equals u. Sorry, union of u equals u. Oh, no, that's actually a thing in set theory. Well, this is just the set u is just an empty union, I suppose. Is that the right word? Because it's not, I mean, you could think of it as u union u. And, well, okay, that's enough, right? that should suffice. So, lemma 1.8, a collection of subsets of X generates some topology on X if the elements of that set cover X, and if for all points, then you can do this. Okay, so these are just some necessary conditions. Let's see, can I prove this? Okay, so one gets proven because we said for the definition of a basis says that every open set can be covered, is the union of some sets inside of that set. So inside of that collection. So, okay, from that, we can say that there exists beta I, well, bi inside of this collection, such that okay, maybe I should say it like this: pick u to be equal to x in, then there exists bi such that, well, bi in indexed by some set I, such that union of bi is equal to x. But that means literally you cover x. that you cover the space x. So there we go. That proves the first bit. The second bit. Okay. So let's see. For all x in the intersection, so maybe if I have two of these, b1 and then b2, okay, then because so So what we're doing here is we're generating any topology. We don't care about whether or not it generates a specific topology. So if there's a point in between x1, I don't know, sorry, some x here, then because I'm trying to develop a topology here, I should be able to find, it should be that B1 and B2 are sort of like open sets, and so their intersection is open. I.e., I could find a little open neighborhood around of it. So let's see. Well, B1 intersect B2. Okay, what am I doing here? I mean, I'm willing to bet that I haven't quite figured this out. I think I just left it as an exercise because I thought it was obvious. And that's kind of normal. I think people do that. So I might go over it next time because it's, maybe it'll just come to me later. I mean, keep in mind, it's like 12 a.m. I'm pretty tired. I'm just going to give it one more thought. So I got B1 intersect B2, then never said anything about intersections, did I? Okay. Yeah, I mean, I don't remember. I think it's something to do with the fact that if you have, I don't know, U being open and V being open, then yeah, okay, maybe it is that. So B1 is open, B2 open, B1 intersect B2 is open, and so it equals the union of some BIs, all right? And so X lies in one of, so, okay, hold on, maybe it's like that. Yeah, maybe that makes sense. Which implies X lies in one of the BI. Call it B3. I think that's how you're supposed to do these things. Okay. Definition 1.9. Given an X and X, a collection, it's called a neighborhood basis of X. If for all U in omega, where X is in U, then there exists a B in the collection such that X is in B, and B is a subset of U. Okay, so it's a bit silly and crazy, but I've given a little picture here. So it says, fix an X whenever I can find an open set around X, U, then I should find a basis element in that U around X. So here it's sort of like saying, hey, here's my space X, take a point, fix a point X. Okay, a space capital X, fix a point little x. Then if ever I have an open set around it, then I should be able to find a little ball, well, a little topological ball around X. Yeah, so show every metric space is first countable, has a counter. Yeah, this is the exercise that I said was not one that I actually thought was that interesting or fun to do, but its consequence is interesting. So the lemma, there's a lemma that you can deduce from this and that is there exist topological spaces that don't arise from a metric. So, I mean, I recommend giving that one a shot on your own. I can't be bothered to do it. Definition 1.11. So you have two topological spaces. You can define the product topology on them, on the Cartesian product of the two sets, to be this new topology, which is defined by the topology generated by the cross of open sets in either space. So we call this basis a set of rectangles, and I think the idea is, I don't know, maybe if you thought of U like that. Oh, I know. Maybe if you thought of X like this, and like Y like that, right? Then maybe that's sort of like your interpretation of U, and that's that's your interpretation of V. So this space that you're really talking about is kind of like that. That's like an open set, or at least one of the basis elements of our open sets here. So it kind of looks like a rectangle when you frame it this way. I don't quite like looking at it like that. I kind of prefer the most rigorous definition of it, but it's up to you. This is a nice exercise where the standard metric on R, like the metric for Rn, is the same thing as the metric on R cross R n times. But this is also one of those things that I think is okay. Like, it really will only take like 20 minutes, I think, to figure it out carefully. Is there any support in the notes? No. Okay, fair enough. Okay, if you want to see how to do this thing, I suppose you should just comment about it. Definition of 1.14, let X be a topological space and A is a subset of X. Then you can put a topology on this subset induced by the original topology, which is supposed to be the intersection of open sets of that topology. So here, this is open sets of that topology intersecting with the subset. So sort of like if you have, maybe this is your X, maybe that here is your A, maybe, and then this thing here is maybe some open set in X. Okay, so it's open in X. Then we'd say this region is open when you sort of like ignore all of that. It's open in A. So that's kind of the way that you should think about these things. In fact, I gave these nice two examples about disks and balls. So here, you define the unit sphere in the n-dimensional unit sphere, and the n-dimensional unit disk. So a topology can be defined on either of them by sort of just saying, hey, you know what, let's just take the regular topology on R squared and intersect it with literally the unit sphere and unit disk. In fact, you're just going to end up getting spaces that you sort of expect. So for example, on the unit disk, you sort of get stuff like arcs. So on the unit sphere, you get sort of stuff like arcs. And if maybe the unit sphere on in a higher dimension, so maybe like that. How do I draw this? Like this. It's sort of like a region in space that's kind of like on the surface. Let's see if I can draw this carefully. So it's just like a little section of a little open looking section. So it doesn't have the boundary. Maybe it's the union of a bunch of things that don't have a boundary, that lie on the surface. Whereas in the unit disk, it's sort of like, okay, regular open balls inside of the disk will work. Things that sort of don't have a boundary, but lie inside of the disk and fill up some volume of space, those things end up being open. So it's the topology that you'd sort of expect. That's the way I think about it. Just the one that you just take the topology that you already have and just whack an intersection on all of them, and it gives you a new topology. So the topological n torus is defined as n products of S1. So S1 being the circle. So just literally this one here. Wait, is that S2? No, it's S1. That's S1 because it's it's like a line, so it's one-dimensional. And if you think about what the n torus literally is, am I right here? Should it be S2? Should be disks? I think I'm fine. If I'm wrong, someone will point it out. It's just the n product of S1s. And the interpretation you're supposed to have of it is that it's sort of like thinking about an n-1 hold donut. I just want to point out, this is supposed to be the donut in these notes. So if I'm a bit confused, this thing here corresponds, like if you just subtract 1 from this to get the number of holes. So I think I'm right about that. I hope I'm right about that. Is it S2? I think it might be S2. Sn minus 1. S1. I don't know. I'll check this a bit later. Maybe I'll check it now, actually. Yeah, no, it's good. It is actually the end product of circles. I got a bit worried for a second. It does make sense because it's sort of like thinking, well, okay, if you want to think of the donut case, for example, just the specific donut, then it's sort of like stacking circles among each other in a circular fashion. And, well, that's sort of like maybe taking a cylinder, right, which is like that, and then connecting the sides because it's supposed to be a circular product, I guess, of circles. So it would sort of be like a cylinder that sticks to itself. So sort of like that. So yeah, maybe a bit confusing. Even I get confused about this sort of stuff. But that's okay. At least we have a definition for an n-torus, and hopefully in practice this will actually be easy to use. So x and y are topological space. A function is called continuous if the pre-image of open sets in the second space, y, is open in x. In such a case, we say f is a map. So this is weird because we have this nice intuition about what continuous means in a metric space, or maybe you could think of it as like literally x and f of x functions, r to r functions. Like we think about how continuous sort of means you can draw a function without taking your pen off the page. But you might think of surfaces in high dimensions, maybe like a manifold that's kind of like this, and you think to yourself, this kind of looks like the result of some sort of function, right? That just maps points up like this. So maybe this is your x, maybe that's your y, and that's your z, and it just takes x, y's up to points like f of x, y equals z. And then what you end up getting is some sort of surface here instead. And you might think to yourself, is that thing continuous? Is f of x, y continuous? And in metric spaces, you come up with this idea where it's sort of like saying, in all sense of continuity, you sort of ask yourself, if I move a bit, say I want to budge a little bit up and down by a fixed amount, how far can I move a little bit can I move a little bit left, right, up and down in my domain, just a little bit, so that I can go at most that high up and down in my codomain. And I've left it as an exercise to argue that this sort of notion of continuity that we have in a metric space, which is defined through balls, is equivalent to the proposed statement. And I don't think it should take too long. The idea is, all open sets contain balls in a metric space. So if you have, I don't know, an epsilon ball in Y, so I don't know, maybe you have maybe you have something like that in Y, then you need to be able to find by the definition of continuity, how the fuck do I say this? Okay, you can find some sort of little delta ball around X in so this is subset of Y, and then this is a subset of X. The notation here is getting a bit ugly, right? But it's sort of like saying this thing, the existence of a ball. Wait, no, what am I trying to do? I should be able to find a little ball that implies that you're inside of a little ball there. I don't fucking know. It's something like that. I've written down some of the details on what you're actually supposed to prove right here, and you sort of just work off of it. Like you just say, you just use the fact that open sets contain open balls in them. But I did this like 3 or 4 times last year, and I can't be bothered to prove it again. I mean, I'm saying this like I'm Fermat, as if I can prove it randomly on the fly. I think maybe I've shown that I can kind of prove these things on the fly. It just takes me a bit of time, and I don't really want to waste too much of it, being that we have so much content to go through. So remark, you can place the word open with the word closed in the definition above, and its equivalent. And the idea is the complement of open sets is a closed set, and complements work very nicely with the pre-image operation. So I recommend you just try that. It does end up working. So the above exercise implies all continuous functions that you know using epsilon delta definitions are continuous. And well, yeah, that's sort of the point of doing the exercise. I gave a little nice example of, and because of that, you can actually argue that these regular metric space sort of functions that you would have understood before, they are still continuous. So x mapping to modulus x over modulus of x is a continuous function. So no, is not a continuous function because it's sort of like it blows up around 0. That's so you'd expect maybe around 0 for somehow intuitively to think that it goes to infinity, but there's no such thing as infinity when you're going from Rn to Rn. So I guess it's kind of broken. It's a bit broken. All right. Pasting's lemma: if X is the union of two open subspaces, then and the restriction to each of those closed subspaces is continuous, then f as a map from X to Y is continuous. Okay. All right. How do you prove this again? I suppose what you can do is you just think to yourself, hey, yeah, because even in the notes they list this as an exercise, and I think I tried it. So the idea is take V subset of Y, and we say it's closed. So I'm using the remark here that I can replace the word open with closed. So take V closed in Y, then by the continuity, what am I doing? It's F inverse. F restricted to A inverse of V is closed in A, and by definition of what it means to be closed in a subset, it's closed in and because A is closed, the arbitrary intersection of closed sets is closed. So this is closed in A and therefore it's closed in X. And ditto with B, I could just change this to B here. Change it to B here and change it to B there. So that means this. It's the same sort of argument. And then what you say is F restricted to B inverse V union F restricted to A inverse. Okay, well, the union of two of finitely many closed sets is closed, and so this is still closed in X, and you just argue that this is equal to F inverse of V. So, yeah, I think that's enough. I'm hoping this argument's right, or it's at least close to the correct argument. I never really checked it. I'm kind of freestyling. So if I've got it wrong, please feel free to comment and just tell me I'm an idiot. Okay, definition 1.25. Let X and Y be topological spaces. A map F from X to Y is a homeomorphism if there's a map G from Y to X such that that and that You might actually recognize this as just saying g is just an inverse function for f on the right and an inverse function on the left, which is just saying that g is an inverse function of f. And here we argue that, well, in the definition we assume that g is continuous. So in such a case we say, x and y are homeomorphic if such a g exists, but this is really just equivalent to saying that there exists a function from x to y that's a bijection, and it's continuous and has continuous inverse. And showing that this property here, saying that these two things are homeomorphic, is a equivalence relation on the set of topological spaces is not hard, because, well, you're homeomorphic to yourself by the identity map, and if you're homeomorphic, I don't know, maybe by f to y, and then homeomorphic from y to z by g, so as in the maps kind of go like that, then g composed with f is a homeomorphism from, like this way, from x to z. And it's not hard showing that this actually is a homeomorphism. You just check that the open sets are preserved under the open sets are preserved knowing that f and g are open. So we've got transitivity. If x is homomorphic to y, then then there's a continuous bijection whose inverse is also continuous. So if I went from x to y by f, then y to x, so y to, what am I doing? Y to x by f inverse is a homeomorphism from y to x, I suppose. And so the top line would have said this implies y is homomorphic to x. So yeah, this is really not that exciting. It's quite straightforward. You just have to show that something is an equivalence relation. Okay, so x to x squared is not homeomorphism from R to R because it's not a bijection, but the function below, which is the cube of a real number, is obviously a homeomorphism because it's continuous, it's got an inverse function, so it's a bijection, and the inverse function is just cube root of x, which is obviously continuous. So there was an exercise in the notes that was quite nice, and that was to show the n-dimensional cube is homomorphic to the n-dimensional disk, and well, unit ball, if that's what you want to call it, the n-dimensional unit ball. And I don't know, how do I argue this? Well, the way I thought about it was, what you sort of want to do is compare balls in maybe a smaller dimension and just hope and pray that like it works in a higher dimension. So, I mean, in is supposed to be 0, 1 to the n, and obviously by some sort of translation, okay, I can sort of turn this into -1, 1. Oh, okay, translation plus a stretch. I can turn this into that, right? And if I think about this in the case when n is equal to 2, it's sort of like saying this little, I can fit a square outside of my unit ball. Okay, I thought to myself, maybe what I want to end up doing is, okay, let me just get this right. So, I mean, it should be touching, but I'm an idiot and I'm kind of drawing this badly. What I want is a function that sort of preserves these endpoints here. And so that's the center here. Maybe, yeah, map the center to the center. Maybe take a point, maybe like there. And in some sense, in here, it makes sense, but I want to scale it so that it makes sense somewhere with respect to length inside of a square. But you could think of a square as just a ball with the infinity norm, and the unit disk to be the ball in the with the to norm. So what you're trying to actually end up doing is convert points. Well, we're just trying to find a map from like one kind of ball with respect to some with respect to some metric to a different kind of ball with respect to some metric. So if you thought about that enough, you might end up with the function. You might end up arguing to yourself, hey, I need to think of a function f that takes me from. Okay, let's go from here to here. That sort of preserves. That sort of takes the. That sort of sends me to a new sort of norm. So I want to end up taking v from the to norm to the infinity norm. So the to metric, I suppose. So, I mean, I could say norm because it's translation to the center, and translating to the center makes it less about distance and more about length. So whatever. I'm going to assume I said norm here. Yeah, I would want to try and squeeze out the to norm. No, turn a point from its to norm to its infinity norm by sort of stretching and going along lines. That way I have a unique representation, because there are a lot of points that end up having the same to norm and same infinity norm. They're all points that lie on spheres. So you could come up with this idea where what you want is f of x infinity to be equal to x2, and you want to stretch it along the lines. So you could think of f of x equals, okay, so how do I do this? I want to scale x. I want to cancel out infinity norms when I take infinity. So if I did that, if I took an infinity norm around this, I'd have to, well, that's a constant, I put an infinity norm around that, so I'd cancel this out. So it's an infinity norm on the bottom somehow, and I want to use the to norm instead. And this should do it, I think. If it's not that, I think it's also f of 0 is equal to 0. That will help. I think that's supposed to be the map, if I'm not mistaken. And that's an explicit homeomorphism from D to IN, and I leave you to just sort of fill in the details from here on. Okay. You know what's funny is that they mention this theorem called the invariance of domain by Brouwer, which says that two n spaces, okay, not 2n, comma, like not two n spaces, but two lots of n spaces with real entries, they're the only kinds of objects, two lots of n spaces are homeomorphic if and only if they are the same n, which when I say it like that sounds wrong, but if you read it like this, it's much better. So maybe I should stop talking and give you guys a minute to actually see what's been written here. There's an exercise that says, show that the two torus, so the one-holed donut, is not homeomorphic to the sphere in 3 space. So the sphere that's like, you know, the boundary of a sphere, I guess, or whatever you want to call it, you know. Just not the circle, the bigger one, you know, the surface of a basketball, if you will. A basketball without a puncture. I know that one of you mentioned this, it hurt me, okay? Hint, you will struggle to do this without fundamental groups or algebraic topology. Well, because I am well versed in algebraic topology, I can just say use the homology group, and that's easy enough, but you guys don't know what the fuck that is, so the point of this is it's actually just a bit of a joke to myself. You can't really easily show this. I don't actually know any other way to do it without fundamental groups or algebraic topology. In fact, this actually brings up the point of sort of topology, and that's sort of to find all shapes up to homeomorphisms. But doing this is not easy, because what you want to try and end up showing, like, it's hard to write down explicit homeomorphisms. So you would hope it's easier to show that two things are not homeomorphic, right? But it turns out trying to prove this negative is a bit of a pain in the ass. There are a bunch of things that you could try and do. So, what you want to end up doing is show properties that are invariant under homeomorphism. And that is because, I don't know, maybe say it's like a x, oh wow, maybe x and y are homeomorphic, and then I end up doing something and I get some structure, I don't know, a of x and a of y, and I expect I don't know, maybe this has a property here. I expect that through homeomorphisms, after doing some sort of operation, yeah, I mean, how do I say this? It's like connectedness. Yeah, I mean, what you'd expect is a property to sort of be preserved. Like this property would somehow be preserved. I don't know. Okay, maybe the best example I've got is connectedness. So maybe if x and y is connected, okay. If x is connected, then and f is a homeomorphism, then I'd expect f, what's it called? F of capital X, the space after you've bijected it. So maybe homeomorphism to y, which equals y, is connected. So what I've done is I've taken x, I've spammed a homeomorphism. I said this has a property, and then I say because this is a homeomorphism here, this thing has a property. So there's a handful of these ideas, and that's like connectedness, the number of connected components after a point is removed from each set, compactness, these are all normal things. But a more sophisticated idea is to have an algebraic invariant. That is to say, take two sets x and y, but this diagram is obviously inspired by martingale. Then if they're homeomorphic, if I do some sort of operation and I get an algebraic structure like a group, or I get maybe some vector space, maybe, I don't know, I get a matrix, then this, so this is a homeomorphism, then I'd expect these two things to be isomorphic because they're algebraic structures now. So the examples that I've given here are fundamental groups up to isomorphisms. If they're isomorphic, then yes, we'd expect them to be homeomorphic. And homology groups up to isomorphisms, except that's more algebraic topology. Granted, this is all sort of algebraic topology, but it's an introduction to topology, so you only get to see one algebraic invariant for this entire course, and that is the fundamental group. So we're going to get around to that at one point or another. But homology groups, yeah, not quite. That's if you're stupid and crazy enough to do algebraic topology, in a few weeks you might end up seeing a video about it by me. So yeah, stay tuned for that, I guess. Okay, and I think that covers like a bunch of the preliminary stuff. I think up to when I talked about Brouwer's theorem from 1910, that was all preliminaries, and this was sort of talking about how to classify shapes, because what you're trying to end up doing is showing two spaces are homeomorphic or not. The idea of homeomorphisms is sort of just to say that you can squish one into the other without tearing, gluing, or cutting, or any of those weird things. So yeah, there's no easy way of like immediately drawing why it's true. I mean, I can think of a picture as to why that's true, but trying to draw it is a bit difficult without sort of saying, well, a coffee mug, when you squish it, little regions around it don't get sort of like thrown apart too hard. So yes, there is a homeomorphism between a coffee mug and a donut, but or at least its surface. But it's a bit tricky to write it down. You just sort of have to think about it a little bit. You can squish one into the other, and the idea of a homeomorphism is exactly that property. All right, disjoint unions. Let X. Suppose you have a family of topological spaces indexed by some indexing set. The disjoint union is the topological space with the underlying set that. Okay. Its topology is generated by sets of the form open sets cross an index. And the index would correspond to the open set it actually corresponds to in its corresponding topological space, I guess. Maybe I said that wrong. I spoke a bit fast and thought a bit in a bit of a rapid fashion. Okay. So this is like the normal union, except with an identifier which tells us which topological space it comes from. Indeed, given a topological space X and the space of a single point, star, they usually use star for single points, then X cross star with the product topology is homeomorphic to X itself. So this is to say that they basically have the same topological structure. So kind of neat, but they're not exactly the same thing as unions. So there's some examples here. X union X is just the set X, but the disjoint union is sort of like taking the union of two disjoint copies of X. So here I've got X, but it's indexed by 0, and X indexed by 1. There's also this other example, which is taking half open intervals. If you take the union of all of these half open intervals among all integers, you basically just sort of patch up. So maybe I can think of it like this. So you got 0, 1, 2, 3, -1, -2. And so I've got open sets. Well, I've got half open sets like this, but then I also have that there. Okay, and then I can do the same here, so I can get a little thing like that. Right, and if I can go like this forever, and if I drop down all of these lines, I sort of get filled in points everywhere. So what I actually end up getting is the real lines if I end up collapsing this all down with each integer. So yes, I can argue rigorously and non-rigorously, but I think this intuition actually helps. If you were to argue this rigorously, what you'd end up saying is you have the union of a bunch of subsets of R, and so the union on the left-hand side is a subset of R, and any point in R is either an integer, in which case it's if it's an integer I, then it's in xi, and if it's between or it's not an integer, in which case it's between two integers. Suppose the integers it's between are k and k plus 1, then it lies in x sub k, and therefore it lies in the union of x sub k. So you could say R is a subset of the left-hand side. So yeah, kind of obvious. The disjoint union, however, of xi, oh, maybe I wrote this wrong. Okay, yeah, I could probably fix this. The disjoint union of xi's is just supposed to be the union of I and z, such that xi is identified with I. But the thing is, each of these xi's is a half open interval, right? So maybe if you think about it like that, 0, 1, 2, 3, what you've actually done, -1, -2, okay. So at 0, I end up getting the half open interval from 0 to 1. So I get something like that. Maybe I drew this wrong. Okay. 1. And then I get, when I is equal to 1, I get the half open interval from 1 to 2, right? Like that. And then I should end up getting something like this. So I get a hole here, and like that, and a hole here, and then like that. So this is what the disjoint union looks like. Here it collapses all down to, R, whereas here there's nothing to really collapse it down to, because all it is unions of these things, and these things are just actual objects in R squared space. So actually, if I drew this properly, this would be y here, and these would all be sort of like coordinates. So there would be 2 here, and so on and so forth. I can kind of go left, I can kind of go right. Okay, well, bro, that's left and that's right. Okay, so that's disjoint unions. So before university, topology seemed like a study about mushing shapes from one form to another without cuts or tears. This is encapsulated by a homeomorphism, as I've already said. Homeomorphisms can be used to classify what sort of shapes there are. Any child can tell you that we can form new shapes by gluing bits of the shape together, since gluing would violate injectivity, because remember, when you have a homeomorphism, you could always have the identity map from from a space to itself as a homeomorphism. But if you maybe identified 2 points as being the same, then that same homeomorphism sort of fails its injectivity criterion now. So since gluing would violate injectivity, any of the new, what the fuck did I write here? The new glued structure isn't homeomorphic to what we started with, literally giving us a new shape. Okay, it's giving us a new shape up to homeomorphisms, but whatever. So we're going to sort of try and understand how we can get new shapes by this notion of being able to glue things together and getting something that's no longer homeomorphic to what we started with, because our homeomorphisms just broke. I mean, it's not entirely that if you glue, I mean, what you could do is you could glue every point to itself and you get a new space, and then that's, exactly, it's sort of like rewriting the same space, because, I don't know, if I gave you a sheet of paper and I said glue every point to itself, all right, you would just sort of like leave the paper alone because it's already glued to itself, right? If you said that, every point is glued to itself, it doesn't really change how it looks. It behaves exactly the same way. However, if I did ask you to glue the corners together, then, you're going to get something that looks completely different. Okay, well, not completely different. Completely different up to homeomorphisms, blah, 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 okay? Recall an equivalence relation on set X is a subset E, blah, blah, blah. I'm assuming you understand what equivalence relations are. If you don't, holy shit, that's just first year stuff. But the point is, an equivalence relation just defines a new way of saying two things are equal. What you might have forgotten is the set of equivalence classes partitions the original set. So that would make sense. I think it makes sense intuitively, because maybe this is your space X here, so maybe these things are equal, this one and those things are equal. So maybe let's say this is E1, this is E2, E2. So like this is the same space, but they've kind of been disjointed or something like that. And maybe everything else is E3. Right. The point is, if you're equal, right? If you're an equivalence class, you're just the set of things that are equal to any one of any members. So maybe if X here is that point, then Y here is in the same set if and only if x is equivalent to y. So, and if you're equal to one another, you can't be... Things in your equivalence class can only be equal to you, so everything outside has to not be equal to you. You know what I mean? Which means that you sort of have this categorization of every element in the set X, and they can only lie in any one of these equivalence classes as a result, because they can't be in two equivalence classes, or else they'd be two things that are supposed to be equal, in which case they'd be in the same class, right? I mean, I'm explaining equivalence classes as if you're a child or you have no experience with these things, but assuming that you do, I think this is kind of nice and it's quite straightforward. This object, so X, this is going to be used a lot. This is our equivalence relation, and that's our original space. This is supposed to be the quotient space, and it's the set of all equivalence classes that we have. Okay. But what's really nice about equivalence relation is that previously unequal objects are forced to literally be the same object in a new space, in this new space at least. We call this the quotient space. So it actually does give you the same idea of gluing things together. The real question would be, does it preserve some of the nice open ball properties? Can I like take a little neighborhood around it and it still kind of looks open or whatever? And the idea is, yes, you still can, but it requires a new sort of because you've defined a new space, the quotient space, you need to define a topology on it. And you're hoping to find a topology that's extremely natural and preserves all the properties that you would expect to hold. So, and really extremely nicely to the original topology. So, yeah. So I gave a couple of examples here. Here's an equivalence relation that identifies the left side of a square to the right side of a square. And if you think about the quotient space, then it's sort of like saying I glued this side here to that side. And because this is just a filled-in square, all you're going to end up getting is a hollowed-out cylinder as a topological space. Granted, I haven't stated what the topology is, but just take my word for it. Maybe you also think of the unit interval and you just equate the 1 and 0 and say everything else is just equivalent to itself and nothing else. Well, then it's sort of like saying, hey, 1 and 0 are the same, so just glue them together and everything else stays the same. So if I glue them together, then it's sort of like just getting a circle together again. So yes, keep in mind, this is a new space, and there is some abusive notation that kind of goes on whenever you're reading John's notes. So I mean, if you read my notes, I'll probably point out any abusive notation, but I can't say that these great mathematicians care about if the notation is easy to read. So yeah, there's that. Okay, definition 2.6, let X be a topological space and this be an equivalence relation. The quotient map this is the obvious map that you would expect. You just take an element to its equivalence class. From that, we define the topology on the quotient space, and it's just the objects such that it's just the space of open sets. No, it's the space of sets whose pre-image under the quotient topology remains open. So i.e., it is the set of objects in the quotient topology that forces the quotient map to be continuous in the traditional fashion, i.e. pre-images of open sets are open. So, and that is literally what this says. It's like Q inverse of V is open in X. It's the V that whose pre-images are open. So we say those are the ones that the open sets. So in every facet, it's literally just the topology that makes Q continuous. Okay, so this is the obvious way of preserving topological properties from X to its quotient topology. Indeed, by definition, we can force that the quotient map is continuous. Okay, I've already said this. Exercise. Suppose that this diagram between topological spaces commutes, so F is equal to G compose is equal to Q compose G, and Q is the quotient map. Show that F is continuous if and only if G is continuous. Okay, so the idea would probably be F is equal to G composed with Q. Okay, so F inverse of an open set in Z. So maybe U sub Z, U is open in Z, is going to be equal to G. Okay, well, that would be Q. Is it G composed with? No, sorry, I'm wrong here. This is supposed to be Q composed with G here. Q composed with G inverse of U sub Z. So this is just coming from the definition, but this is the same thing as G inverse of Q inverse of U of Z, which is equal to G inverse of Q inverse of U of Z. Oh shit, maybe I was right initially. So I do Q first and then G, right? Oh shit, yeah, I'm wrong. Okay, let me just fix this. Sorry. I was gonna say this looked wrong because I have done all of these problems before, but I haven't really like listed them anywhere that I like would remember. So they're just sort of kind of half written in my head somewhere. Yeah, this is right. Okay. All right. So suppose I want this to be this is open if and only if this thing is open, right? And by the definition of Q and the quotient topology, this is open, okay, if and only if this is open would imply that that is open, okay? And if that is open, then by definition of the quotient topology, this object is open, i.e. F inverse of U of Z is predicated entirely on if G inverse of U of Z is open. Oh wait, being open. So it kind of just spits out. So yeah, this would suffice to show that F is continuous, because being continuous is just saying pre-images of open sets are open, and this would suffice for showing that G is continuous, because pre-images of open sets are open if you're continuous by definition. So F is continuous if and only if G is continuous. Simple as. Exercise. So I thought I'd change the way the problem was stated here, because I kind of didn't like that there's some details that are kind of thrown out the window, and I decided I would just make them a bit clearer. So R squared quotient Z squared is a quotient group, but all quotient groups are quotient spaces, i.e. you could take G. You could take a quotient, the set of quotient groups, and say it's isomorphic to G, the quotient space on G, where the relation the equivalence relation is if G1 is equivalent to G2, if and only if G1 inverse G2 is in H. So H being a subset, a subgroup of G. And you can define the group relation on the quotient to be, well, the obvious thing. So, yeah, you can think of this as sort of a quotient space. And you can argue that quotient space is somehow not isomorphic, because it's a quotient space now. So it's a topological object. It's homeomorphic to the donut, the torus with one hole. And, how do you prove that? You just realize that there is this nice identification. So wait, hold on, maybe I should... There's this nice identification with the unit square, which is, okay, if you've done any sort of like thinking about this, you might have thought about how this is sort of like modular arithmetic in that, it's like modular arithmetic in that if you go this way, eventually you'll end up back here. And if you go this much, so if you go this way, then you'll end up back here. So it's sort of as if going from here, so if going up here a little bit is the same thing as going up from here a little bit, then maybe you should just think of it as you glued this end up to this end and you just took a small step over it. In the same way you kind of do it with these two sides, and when you sort of like glue these things together, you get a cylinder, so sort of like this, where it's kind of been glued, and then you sort of okay, so how do I draw this? This is fucking annoying to draw. You sort of glue these two circle bits for the cylinder, you know, the rim of it, I guess, together, the straw rim, if you will, to get a donut. Kind of looks like that, and you could just maybe see it like this, like that. Not the best drawing, but I hope it makes sense. That's how you'd you can write the explicit bijection down, but I can't be bothered to explain it. An identification map between x and y topological spaces is a map from x to y such that for any open set in Y, it's open if and only if its pre-image is open and it's surjective. Okay, so it's really close to being a homeomorphism. The only difference between this and a homeomorphism is that it's a bijection. But remember, when you're doing quotient spaces and stuff, you kind of lose injectivity. So it's like you can get all of the topological properties you want, but you're not exactly the same object. You kind of identify as being practically the same topologically, though. So, yeah, identification maps are quite nice because, well, you know, if I asked you to prove something about a torus has a really ugly parameterization. I haven't actually written it down. I think it's in there. I think it's John actually did write it out in his notes. And are you telling me you really want to use the metric space definition of a torus or think of it as S1 cross S1, when instead you could just think of it as a square and gluing two sides together twice? Like they're not. It's not that bad thinking of the square. So yeah, there's that. There's a proposition. A surjective map is a identification map if and only if topological space, well, for all topological spaces Z and for all functions G from Y to Z, G composed with F is continuous if and only if G is continuous, i.e. this diagram here, the one, of course, this one commutes in continuity. So how would you prove this? Exactly the same way you prove this. You just say, hey, you know what? Suppose, okay, what am I supposed to do? Okay, I have a topological, I have a subjective map, I have a subjective identification map. Pick a topological space Z, pick a function G, which maps Y to Z, then argue that G composed with F is continuous, because pre-image, well, it's in the inverse of an open set is the composition of the inverse function of F applied to inverse function of G. Should I say inverse function? Okay, pre-image of F applied to pre-image of G, applied of a open set in Z, and because F is a subjective identification map, it's continuous. Oh no, it's a open sets correspond to open sets in Y, and so you would hope and pray that the G would hand over open sets from Z to Y, so that Y can pass it to Z, Y can pass it to X through the pre-image of F. So it literally is the same thing, and that's why I've left it as an exercise. I'm just going to point out that homeomorphisms are supposed to be, maybe I should do this. Homeomorphisms are shrinking and stretching operations, whereas quotient topologies are just sort of gluing things together. So hopefully that makes this all clear. So we're nearing the end. We're going to talk a little bit about retracts and deformations. I'll get to homotopies probably sometime soon, but I can't tell you exactly when. So a pair of spaces x, a consists of a topological space x and a subspace a of x. Well, a subset of x. If a is a single point, then we write the pair of spaces like that. Rather, we just omit the set sign and we call it a pointed space. So it's kind of obvious. The first example that I saw in the notes was the entire plane and S1, so just the circle, and the entire plane. That's a pair of spaces because S1 is a subspace of the punctured plane. I mean, you could also not delete the point, and it's also a subspace, but whatever. S1 and the singleton 1, 0. That's a pointed space because the second element, the subspace is a singleton, which is how we defined what a pointed space was. So, yeah, simple as. A subset A of X is, why do I keep saying it like that? A subset of X, A, is a retract of X if there's this map called a retraction, which gives the identity on A when you restrict to A. And yeah, it's just continuous, I guess, because it's a map. Remember, whenever someone says map, they mean continuous function. So this encapsulates the idea of smushing an entire topological space onto its subspace continuously. So why is that? Well, because it's a map, it's continuous, and because it's the identity on the subset, everywhere else is where things sort of get pushed towards the subset. So I think of it like this. Maybe this is your set X, and that's your set A. Then all of these points get mapped to nothing, right? Mapped to the same point. Whereas everything here is thinking, hey, I really should continuously move to inside of here, right? Whereas things far away, they act a bit more dramatic and they try and throw themselves in a bit faster. But remember, we don't want large jumps. Like if I had done something like this, right? and said, hey, there's a point really near this one, but let's just make it jump very small, then it's sort of like, for some reason, if I move a little bit, I have some region in which I move very little, whereas here I moved a lot, which sort of makes you think, nah, this thing isn't really continuous. So you gotta have a decent picture in your own head. Maybe my diagram isn't perfect, but the idea is the image of X is always in A, and everything in A is just an identity map. So it doesn't move anything anywhere. So yeah, it does basically just mean smush the topological space X into A. Yep, so example given r squared, well, the punctured plane, i.e. the r squared without the origin, collapses onto the unit circle. And I didn't come up with it, I'm not a genius, I didn't come up with all of this, is just this map. It just scales every point linearly down. Just keep in mind, R is like very surjective but not injective. Okay, so you don't need this bijective quality that we had before with homeomorphisms and bijective inverses, or sorry, continuous inverses. All you need is a continuous map that takes a topological space to its subspace. So yeah, whilst keeping everything as the identity on the subspace. And you can see that, to be sure, because if you were on S1 here, S1 is just a set of things that have norm 1, right? Well, okay, if you were a unit, so okay, let's see this. S1 could be thought of as the set of X unit vectors. Yeah, the set of unit vectors, right, in r squared, right? i.e. if I did r of x hat, so if I had restricted to S1, then this would be equal to x hat over norm of x hat. But by assumption, and because we're restricting here, these are just the things that are they have unit norm because they're supposed to be the things that lie on the disk. So not on the disk, on the unit circle. And so this thing here is just 1 on the bottom. So restricting to this would just be an identity map. So yes, it is obviously a retract. So how could you show that the interval doesn't retract to the two singletons? Well, okay, suppose they retract. So maybe I'll argue this for you because it's quite easy. Right? Then, i.e. R from the interval to 0, 1 is a retraction. Then R restricted to this domain, okay, is the identity map. Okay, so that means R of 0 is equal to 0 and R of 1 is equal to 1. Easy enough, right? Okay. Then what is the pre-image of 0? Well, R inverse of 0 then is, okay, well, the singleton 0 is the singleton 0. And the pre-image of the singleton 1 is the singleton 1. But points are, or singletons are always closed, so pre-images of open sets here, because I'm assuming it's the, is it discrete topology or indiscrete topology, the set of all subsets, is always open, here singletons in I are not open. So we get a problem here. Any retraction that we have is not continuous of this form, so that suffices. Where can we go with this? There's a theorem by Brouwer that says that the n disk does not retract to the n-1 sphere. And if you actually plug n is equal to 1, that is literally the exercise above, because, okay, d1 is just the unit ball. Oh wait, no, it's d1 is the set of x such that no, it's the set of x such that norm of x is less than 1, right? Which is the interval -1 to 1. Is that right? Damn, did I state that? Oh wait, whoops, what am I doing? Did I state the definition correctly here? So it's the sum. Oh yeah, yes, it's a. Yes, because it's a. If I copy this definition here, it is x in R such that. Okay, there's only one parameter with this, so it's just x squared is less than 1. But that's just the interval -1 to 1, which is obviously homomorphic to 0, 1, because I could just take the map x plus 1 over 2. That's a homomorphism from this. So if I do maybe like this diagram, that's a homeomorphism like that. And I've shown that this thing here is not homomorphic to 0, 1, but S1 is equal to the space x element of R such that norm of x isn't equal to 1. Sorry, less than. And then that should be. Oh no, it is less than or equal to. I'm wrong. So if I do this, then this is just the set -1 to 1, which is homeomorphic by the same map, x plus 1 over 2 to the singleton 0, 1. But that's equal to that, literally. So as we can see, if we follow this diagram here, D1 is homomorphic to O1, which is not homomorphic to this, which is homomorphic to S1. So D1 is not homomorphic to S1. So yeah, it is just it is just the first value of Brouwer's theorem here. So okay. And on to our final definition for today. It's been so far 1 hour 48 minutes of me explaining this shit, and I am on 4% battery, so I'm hoping to get this done. Let X and A be a pair of spaces. X deformation retracts to A. We call A deformation retract of X. If there exists a one-parameter family of functions f of t, which map from X to X, such that, I don't know, I'll call t the time. At time 0, you just have the identity map. At time 1, you end up mapping everything to the subspace. And at any time, if you apply the function inside of the subspace, you just get an identity map, i.e. it kind of looks like a retraction there. So, and the added condition that this is all, like, as a function of two variables, this is an entirely continuous transformation. So what does this mean? It means at time equals 0, you should try and map every point to itself, okay? But then slowly try and push points that aren't in A towards A, okay? but keep everything that's in A mapping to itself as usual. And then at time 1, try and throw everything you can at A like you did before, like a retract. In fact, actually, I mentioned that I didn't end up getting to properly cover this and explain this because I got really tired. This is sort of the idea that a retract kind of just collapses the entire space into its subspace. So this is this f1 of x should be a retract, or at least the inclusion of it's going to be a retract and you apply inclusion to it to get f1, but I'll explain that properly some other time, and hopefully I don't confuse you too hard by having said that. So yeah, this diagram sort of describes how x gets continuously smushed over time. So here we can see that, oh no, that was a mistake. I hate this thing sometimes. Short dots. Okay, yeah. So here everything is sort of just mapping to itself. It gets smushed a little bit more, and then it gets properly smushed onto A. And if you look at the images of ft over time, you start off by just, everything as usual. You collapse it in a little bit smaller, and then its image is just ends up being A. So it literally does sort of just, it's like a slow, steady collapse of the space X onto A. And actually, this will lead on to the idea of a homotopy, which is sort of like, how do I describe one object slowly morphing into another object by continuous transformation? So, continuously varying over time. So, I don't have immediate examples for this. I might have some tomorrow, or whenever I next upload. I hope that this has been intuitive. Yeah, I know it's been a 1 hour and 50-ish minutes, but we covered about 3-ish lectures, and I don't know, it's pretty fun. I hope this has been useful, as fun for you as it has been for me writing this. So I don't know, if I've got something wrong, let me know. Cheers.